Hey, what's up, everybody? Welcome back to the Student Machine Learning Coalition crash course on machine learning. I'm Samuel Pro, and today I'm going to be presenting to you our 12th episode on logistic regression. So before I jump into logistic regression, let's review classification. So when it comes to machine learning, supervised machine learning specifically, there are two different types of machine learning problems that we can solve. There's regression problems, in which you are trying to predict a quantitative numerical value as your answer, and the range of possible values is on a continuous range. And then there's classification problems, in which you're trying to classify a sample into one of many classes, or also called labels. And so today we're going to be talking about classification. And so when it comes to classification, there are many different types, including binary classification, in which you have two different classes that the sample can fall under. So for example, if I was trying to classify an email as either spam or not spam, that would be binary classification because there are only two options. The next type of classification is multi-class classification, in which you have more than two options. So for example, if I wanted to classify somebody's eye color, then I could classify that as black, brown, blue, gray, green, etc. And so you see there are many different options there, and the eye can fall into any of those classes. And so that's multi-class classification. And then there's multi-label classification, in which a given sample can actually fall into many different classes or have many different labels at the same time. For example, if I was trying to classify a bacteria into different classes based on what antibiotic it's resistant to. So for example, if my first class was resistant to antibiotic A, and then my second class was resistant to antibiotic B, well, it may very well be that we get a bacteria that is resistant to both antibiotic A and antibiotic B, and so it receives both labels. And so that's multi-label classification, in which your samples can actually have multiple labels on them at the same time. And then finally, there's imbalanced data sets, in which your training data is imbalanced. So that means, for example, if I was trying to train a machine learning model to distinguish 4-leaf clovers from 3-leaf clovers, but I only, in the training data that I gave it, I only give 20% of my samples are 4-leaf clovers and 80% are 3-leaf clovers, well, there's going to be a bias towards choosing 3-leaf clovers. And even if your model just assumes that all clovers are 3-leaf clovers, it still has an 80% accuracy based on the training data that you give it. And so it doesn't matter that the majority of clovers out in the world are going to be 3-leaf clovers and not 4-leaf clovers, because when you're training your model, you want it to actually be able to distinguish those 4-leaf clovers from the 3-leaf clovers. And so you want to have 50% of your training set to be 3-leaf clovers and 50% to be 4-leaf clovers, so that your data is not imbalanced. And we can deal with imbalanced data using techniques such as SMOT and class weighting, but I won't get into that in this video. Okay, so now that we've reviewed classification, let's practice and see what type of supervised machine learning problems these are. So is it regression or is it classification? And if it's classification, what type of classification problem is it? So just take a moment to pause the video, think about what your answer is, and then come back as soon as you're ready. Great. So the first problem, biologists want to predict which DNA mutations are harmful and which ones are benign. So this is binary classification because there are only two options here. The DNA mutation can either be harmful or benign, and that's it. Okay, next question. You need to train a robot to recognize what numbers from 0 to 9 it sees in a photo. Okay, so this one's a little bit tricky because you may have seen the numbers and then immediately thought regression. But actually, this is a multi-class classification problem because actually there are only 9 discrete options here. The range of possible outputs is not continuous. Rather, there's only 9 options, or 10 options, I mean, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And so you can just treat those numbers as classes, and that's why this is a multi-class classification problem. Okay, next one. If I drive for 1,200 miles, how much will I have to pay for gas? So this one is actually the regression problem, because the amount of money I pay for gas can vary across a continuous range based on the features that you give to your algorithm to train your model. And so if I drive for 1,200 miles, the possible amount of money I can pay for gas can be anywhere from like $50 to $150, depending on the price of gas and where I'm going and everything else like that. And so, as you can see, this is a regression problem because our answer is going to be a numerical value and the range of possible outputs is a continuous range. Finally, we have given how many hours each student studied for it in preparation, will that student pass the exam? And unfortunately, as we know, there are only two options here. You can either fail the exam or pass the exam. And so that's why this is binary classification as well. And luckily enough for us, we're going to be talking about binary classification today for the most part. Because even though we have all these other classification algorithms or classifiers listed here, today we're going to be talking about logistic regression, which is the most fundamental and basic classification algorithm. So what exactly is logistic regression? Because you may have seen the word regression and then thought to yourself, oh, this is used for regression problems. Well, actually it's not. It's used for classification problems, mainly for binary classification, although you can use it for multi-class classification as well if you like. But the regression part is a little bit misleading, so I would just recommend ignoring that part. As for the logistic part, we'll get into that in just a second. And I'll make sure that you understand by the end of this video. So right here we have a logistic graph. This is what you're going to be training your model with logistic regression. So some people ask, why not use linear regression when it comes to binary classification problems? Well, the reason is that linear regression really isn't designed for classification problems. It's designed for regression problems. And the reason why is because in classification problems, particularly binary classification problems, you're only going to have two possible answers that you want your model to come out with, right? In this case, it's 0 or 1, because usually we assign 0 to false and then 1 to true in the case of a true-false binary classification problem. But if it's just like red, blue, or something like that, you can assign the numbers however you want. And so if we use this line of best fit or linear regression model, then what exactly does it mean when the line is above 1 or below 0, right? If we feed it our x variables or our features, and then it outputs like 3, what is that supposed to mean? And you could like say, oh, when the line is above 1, that means it is 1, and when it's below 0, that means it is 0, and try to like finagle the graph in that sort of way. But this logistic curve on the right does a much better job of meeting all our needs because it's bounded between 0 and 1, and also it's a curve, and so we can interpret the y value here to mean the probability that the sample falls into the 1 class. And so using that sort of logic, we can use this logistic regression curve, set a threshold of what percentage we want that this sample will fall into the 1 class we want to use as our baseline. A lot of people use 50% as their threshold. So for example, if the model said there's a 50% probability that this sample is going to fall into the 1 class, then if you set your threshold at 50%, then the model is going to say that this sample falls into the 1 class. And it's the same for whatever threshold you pick, whether it's 60%, 40%, and you can vary that based on your problem and the types of needs that you have. Okay, so what is the math behind this graph. And it's not super complicated to visualize because I'm sure you've all heard of the logistic growth equation in math class. And that's the same equation, same basic function that we use in logistic regression. In linear regression, it's essentially just a y equals mx plus b line, except instead of m and b, we'll use beta 0 and beta 1. Those are called our regression coefficients, and those coefficients are what determines what that linear regression line looks like. Well, now imagine that we plugged in this linear regression equation into our logistic growth equation, and voila, we get our logistic regression function right there. And so the real deal here is, what are those unknown coefficients? And the way that we figure that out is using the maximum likelihood estimation, which involves linear algebra, so I won't explain how it works. But all you need to know is that it figures out what those unknown coefficients are so that we can get the best fitting logistic growth curve for our data. Now, this is a little bit simplified. In real life, if you have multiple features, you're going to have a lot more unknown coefficients, but the concepts are the same. And there's the MLE if you're interested.